Welcome back. Chapter 2 on AC to DC conversion. What is the name for this AC to DC conversion? We call it rectification. Yeah. So the converter or the device that do the job is known as rectifier. So you can see that rectifiers actually appears in our daily life. What is that? Anyone? What is the rectifier that you use it every day? What is this? What is that? You've been using your mobile phone charger, your laptop charger, anything that you need to charge with your battery that is considered as a rectifier. Why is that so? Because the outlet from the wall or the sockets, they are all supplying AC. Yeah? So they are supplying AC, and you know that the battery is DC form. So it's from AC to DC is known as rectifier. So where is this rectifier? It's inside the plug. So it's very small, isn't it? The plug itself is the rectifier. So other rectifiers that you can see in the picture here are like small IC, integrated circuit, with 4 pins, and some with just look like normal diode, but they are rectifier. Square shapes, cuboid, bridge rectifier. So different types of rectifier for different applications. So let's have a look at what are the overviews and the introduction. Okay, just now we have gone through here. We have single phase and 3-phase. In single phase, we have 2 types. One is half wave and another one is full wave. How to differentiate between half and full wave? Anyone have seen the sine wave before? Sine wave looks like this one. So one full cycle, you have the positive half cycle and the negative half cycle, right? So full wave means what? Consider the full cycle. So that is full wave. Half cycles, only half wave. Half. So this is half cycle, and that is full cycle, one full period. Okay, so that is for half cycle. This full wave is for full cycle. So if you are applying different loads to the rectifier, if it is a pure R load, that's very simple because you know that R is basically is a constant, right? So the voltage and current will be the same because voltage divided by a constant number, you get the same thing, right? But if you have the inductor RL, resistor plus inductor, then the story will change. The current will not be the same as in the voltage form. Why? Because you have to remember that you learn about L and C, both of them belongs to the passive components, right? What is the characteristic of these passive components? They are, it looks like a pumpkin to me. No, it's not. They are what? Component or device that is able to charge and discharge, or store and release charges. Okay, but what about R? R cannot. R is only consuming the energy, right? The power, or it would just dissipate as heat. But L and C, they have different characteristics. They can charge, they can be charged and can be discharged. So it will directly change the waveform of the current and voltage. So it will be a different story comparing R and RL. And then if you have another DC source connected to the load of the rectifier, then it will be another story again. Okay, so 3 of them that we're going to see. What about if you're adding another diode inside? This is known as the freewheeling diode. In short, is FWD. So in chapter 2, please, if we say FWD is just a diode, right? Freewheeling diode, that's the name for it. Okay, and I'm going to repeat the same thing for full wave, continuous and discontinuous current, and then proceed with the three-phase rectifier. And then we're going to see, for example, of this DC motor drive. Yeah, the motor drive is to control the motor. Okay, so basically it's a very long chapter. If you look at the pages, it's 104 here. That's why I want you guys to prepare a piece of blank paper. So if you go on, then you can split them into different categories for different family, like half wave rectifier. We have 1, 2, 3, actually 4, because here you see 1, 2, 3, 4, because we have additional DC source here. So you put in the 4 columns and note down the waveforms, because waveforms we have the current, voltage, and the input as well as the output. And then what is the equation associated with each of the category here? How to calculate the DC output, how to calculate the current, etc. So you can list out them, the important equations. Okay, this is just example. You can use whatever material you liked. If you notice here, there's some trigonometry equations there. So you need to refresh back. A few trigonometry equations may involve during the derivation later. Okay, example. Let's start. Okay, now rectifier, if you look at the definition, it's converting AC from the mains or from the TMP for outlet of the socket. It's AC form, which is AC is what? Alternating current in a sine wave. And we want to change that sine wave into a straight line, which is a DC power, by using diodes or by controlling the firing angle of thyristors. Now you see the word firing angle. Thyristor, we know that is SCR, silicon control rectifier. What is firing angle? Remember, firing angle, the symbol of the firing angle is alpha. Okay, so what is alpha? Firing angle is the angle when you tell the switch to start. Okay, before the firing angle, the switch is sleeping, not working. So after the fire, at the moment of the firing angle, so the switch start. What is the switch here? Thyristor. Can we control the diode? Cannot, because diode belongs to uncontrolled. So there is no firing angle for diodes. So the firing angle only appears for SCR. Remember, SCR is the semi-controlled power devices. So alpha is, let's have a look at the picture of alpha. Where's alpha? Alpha. Ah, here you are. If you look at the diagram of the sine wave, this is the input, sine wave. So alpha is the moment we put the pulse, we call it a pulse. We send a pulse to the SCR, which is the gate signal. We send a gate signal at alpha. This is the angle of alpha. If this is 30 degree, then alpha is 30 degree. At the moment of 30 degree, the output will start to work. So initially it's a sine wave, right? So from 0 to alpha, what did I say just now? From 0 to alpha, it's sleeping. Sleeping means output is 0. So after immediately 30 degree, the output will be starting. So it will start here, this point. So it will follow like that and go on. Okay. So at this point, we know it as alpha. Alpha known as the firing angle. Firing angle means you fire. At the point you fire, it starts working. Okay. Come back to that later. So the block diagram of rectifier is very simple. Basically, all the converters, we are using a square box divided by two triangles. And then you just put the sine wave or the equivalent sign as a DC form. So if the input is AC sine wave and the output is DC equivalent symbol. It can be single or multi-phases, 3-phase only we have. Output can be made fixed or variable. If we are using diode, then the output will be fixed because we cannot control. If we cannot control the output, it will be forever the same. If you want to get variable output, meaning that the voltage can change, then you need something that can be controlled. So this fixed refers to diode rectifier. If you want variable output, then you will have to use SCR rectifier or thyristor rectifier by controlling what? There's only one thing that we can control, the firing angle. So if you set the firing angle to start later, so the output will become smaller because the waveform reduce. So where can we use rectifier here? There's a lot of applications here. Example written here, you have DC welder, DC motor drive, battery charger. That's very common thing that you have been using it daily. DC power supply, high voltage DC transmission. So all those requires rectifiers. So you can see that the power application ranging is from very small, for example, battery charger is small power application, and you talk about the high voltage DC transmission that belongs to high power transmission. So the range is very wide and big. Let's see. So you can figure out what you're going to cover. All these. Rectifier is a big family tree that can split into half wave and full wave. And here is only single phase here. So basically rectifier, you have single phase as well as 3-phase. So 3-phase is out of the picture. So here only focusing on single phase. So for single phase, you have half wave, full wave, control, uncontrolled using diode, control using SCR, uncontrolled using diode. Something like this. So full wave, we have two types. One is by using bridge type, another one is by using center tapped. Okay, we'll come to here later. So it's just give you a picture of how many types of rectifiers that may appear in your test or final exam. Right. Anything you want to ask? Let's start with the single phase half wave. Half wave means what? Half wave, we have control and uncontrolled. So we'll start with the uncontrolled first. Come here. No, this is controlled. We want uncontrolled. Let's go here first. Diode. Okay, find the circuit. So where's the circuit? Oh, okay, the circuit is here. On the top left, that is a single phase half wave R load only. R load, can you tell me where's the source? Where is the power device and where is the load? Anyone? Anyone here? Hello?
There is the load.
VS is the source means what? The supply, isn't it?
Yes.
AVS is the supply and the load is?
The resistance.
The resistor. The resistor is the load. And AK is what? What's this?
Diode, Doctor.
AK? Diode. A is anode, K is? What is K?
Cathode.
Cathode. And if we have a supply source, I have a load and diode, the currents flow where? This way or that way?
Positive to negative.
Is it?
Depending on the direction of the diode.
Yes, because this is AC. AC, we have positive cycle, which is the clockwise, and well, right here, the positive half cycle, then the current will be flowing from A to K, right? Is the current able to cross A to K? Yes, because it's a forward bias. What about in the negative half cycle? The current is actually going in the anti-clockwise, go through the load and come to K. Hello, can I cross K to A?
No,
What
It will block.
happened?
Yeah.
reverse bias.
It become reverse bias, so it's a block, isn't it? So it become what? Open. During the half cycle positive, so if you look at the sine wave of the supply Vs, which is the positive half cycle, and this is the negative half cycle at the bottom. Positive half cycle, the current is able to cross the diode. So what do you expect the output of the R? Any output? Yes, so the output will be following the input. Why? Because the R is a constant. So that one is okay. After the negative, this is pi because the first half. So negative half cycle, during the negative half cycle, the diode is open because it's blocking, reverse bias. So if this is open, the circuit it become open circuit. Any current flows through the output or the load, it becomes zero. So output becomes zero. That's why on the pi to 2 pi, this area, it is output is zero. No voltage. The the current is zero because it's open circuit. The output voltage also zero. Is it okay? Then the process repeat. This one is another cycle already. So when it comes back to the positive half cycle, again, the diode will be closed because it's forward bias. So current is flowing. So you have the voltage across the resistor. What is the voltage across the resistor? Basically, V equals to IR. If your I is a number, then you multiply with the constant R, you get the number. That's why you see the shape of the dotted, which is the I current, is the same shape with the voltage. V out and I out is the same shape, but the magnitude is not the same, right? Magnitude not the same. Because what you divide by some numbers, right? So of course the magnitude will become different. But the shape of the waveform, this is known as the waveform, yeah? Waveform. Same shaped, different magnitude. So comes here, the engineering part is to calculate what is the output voltage. Where's the output voltage? Come on. Output voltage, A, B, or C?
B.
Output voltage is written here, right? V out. So output voltage is B. Let's have a look at the signal or the waveform B. It's not signal, yeah? Signal is for electronics. So we call it waveforms. Waveform B, output voltage. The output voltage, is it a straight line? Is it a straight line?
No.
No, right. But then I have a question to ask. When you say rectifier, right, it's changing AC to DC. We know that AC is a sine wave. And when you talk about DC, what do you expect? The waveform should what?
Straight.
Straight,
Straight line.
right. But if I look at the waveform here, I don't see the straight line.
It's a maximum point.
Oh, maximum points you refers to here?
Yes, yeah.
I see. Let me tell you, it's not the case. Oh, don't worry. If you redraw the picture in the next page, right, it is a half wave and then becomes 0. This is pi, this is 2 pi, and then the waveform of the repeat again 0. This is 3 pi and 4 pi. What is the period? The period will be always 360 degree, right? Equivalent to 2 pi t. Now you see, that is the conversion that made from the input to the output. But what we are interested is the DC. So our job is to find the DC equivalent value. Equivalent, is it right? Correct spelling? Okay. So can you tell me where is the DC here? Somebody say that is from the maximum. Which is the maximum? Maximum we say as Vm, yeah? Remember the symbol we use, M for maximum, or the peak voltage, Vm. Okay, so I'm giving you a few choices here. Maybe I can put it the different lines here. One is Vm, one is Vout. Which one do you choose? The DC is Vm or Vout. We're going to calculate, right?
I choose VM.
Out. So the Vout is known as the V average. What is the meaning of average here? DC. Okay, so the peak value is not the DC value. That is the peak value of AC. In AC, if the AC, if we convert it to DC, we need to take the average from the waveform, average. Yeah. So where's the average? You have to take this area. Where is it? You have to take this area, or some part of the area, and you fill the bottom part here so that everyone become same. So it becomes a straight line. So the upper part is filled by the bottom part. So all the areas are filled together. So that line that fulfill up and bottom is known as the average, and it's known as the V out, V average, or DC, VDC. Okay, so you see that the VDC is definitely lower than the peak value. Okay, so in this case, this is the V out waveform. Our job is to find the average value. Where is the average value? VDC. So if you see that the average value is actually to find the area under the curve, or we can use as integration. You see integration? We integrate the waveform, we get the average value or the area under the curve. Okay. Now you see that this is a sine wave, right? So we have to go back to mathematics. I've been living mathematics for so long already. Help me here. How to integrate sine wave? It's a sine wave. We need to integrate sine wave. We get what? Negative cos. And negative cos pi is what? Hey, come on. What is cos pi?
Q1.
Cos pi is what?
It's 1.
1. Are you sure? Cos pi.
-1.
Cos pi is -1. Cos 0 is
1.
1. Sure? Okay. If you're not sure, go back and find your mathematics. You learned that in where? Statistic? I'm not sure. But make sure you know what is a sine cos values here. Sine theta is what? Sine pi is what? Sine 0 is what? Cos 0 is what? Cos pi is what? So now here, why are we integrating from 0 to pi? Any ideas? We want to find the output voltage, so we integrate the waveform. Yeah, okay, fine. Then you're integrating from 0 to pi only. Why? Or because
It's half wave, Doctor.
Because you see, from 0 to pi, you got the waveform, right? From pi to 2 pi, anything there? It's 0. Do you need to integrate something is 0? Redundant. There's no need to do that, right? So that's why we only integrate from 0 to pi, unless you have something here, then you need to integrate. Then we have to divide by the whole range. Which is the range? The range is always a full cycle. What is the full cycle? Can you tell me what is the full cycle here? When we repeat again from the point we start until when the point we repeat again is a full cycle. So we start here and we repeat again at 2 pi. So the full cycle is 2 pi. That's why we 1 divided by 2 pi here. So integrate from 0 to pi, divide by what? 2 pi, which is the whole period. Okay, and the waveform is what? The waveform is actually the input. Input AC, right? AC waveform is Vm sine theta as usual. This waveform is known as Vm sine theta. So here we change it to omega t, so you can integrate Vm sine omega t d omega t. So if you do the conversion using the integration here, I put it notes on the right hand side in yellow box, you can get the answer here, Vm over pi. Pretty simple, isn't it? So if you are not sure on how to do the integration, please revise it immediately. So this is the simplest one. The integration will come harder and harder later, yeah? That's why just now I show you something like can you see that? The cos A plus B equals to cos A cos B minus sine A sine B. This one I also cannot remember, but you need to remember, yeah? Because you need them to do the derivation. Okay, so now that you know how to get the DC value out of these waveforms, this is the peak, this is the average wave value, and the average value is obtained using what? Can you write again? V out or the V average from the waveform, this one, we can write it as, we take it from the whole period, 1 over 2 pi. We integrate from the starting point, which is 0, 0. Starting point is 0, ending point is pi. Why is pi? Because from pi to 2 pi, there's nothing. Nothing means no need to do anything. So in the bracket here, I would like to put the waveform. So the waveform is following the input. It follows input. Input is Vs. Vs is equals to Vm sine theta. Okay, so theta is just a variable. We change omega t here. So Vm, I will just put it in as usual, sine omega t in the bracket. Okay, now you see that Vm is a constant. Normally constant, you can bring it out, right? So you can put it out here as Vm over 2 pi. So integrate sine, what do you get? Integrate sine, anyone remember? Integrate sine, you get negative cos omega t. Now, where did I integrate just now? From 0 to pi. So I put there pi 0. Okay, now, so Vm over 2 pi. So now the brackets come in. You take pi, put it in, minus, because this one is the difference, right, from pi to 0. So negative cos pi minus negative cos 0. What do I get? Negative cos pi. Negative cos pi is negative bracket negative 1 minus negative cos 0. Cos 0 is 1. And then negative become positive. So it's positive plus 1 equals to 2. Does it sound weird? Then the best way of remembering cos would be always to draw the cos sine wave. How's the cos sine wave? This is 0, right? This is 1 and this is -1 for cos. And the middle part is pi, 2 pi. So this is pi over 2. This is 3 pi over 2, etc. So negative cos pi, I want cos pi. Cos pi is -1. So negative cos pi will be 1. And this second bracket is cos 0. Cos 0 is 1. Negative and negative become positive. Okay, now it is -1 inside. Negative cos 0 is -1. So inside here is 1 minus 1. You get how much? 2, right? Inside here is 2. 2 divided by 2 at the bottom, you become crossover. Now, the V out that I get here is Vm over pi. So why did I show you this process? Because this process is known as, anyone can help me? English? What is the name of this process? Okay, derivation is very common in power electronics, okay, in the test or in the final. Okay, the question will sound like, so this is a single phase half wave R load, right? Derive the output voltage. So the output voltage, how to derive? The answer is here. Starting from the first line, second line, third line, and fourth line. That will be the answer. The whole process is a derivation. So in the process of derivation, right, you need to start with all the parameters and do the step by step, okay? If you start by line 1, and then you show me line, final line, and you get 0 for the mark, right? Because this one is not shown, whereby they are important. Okay, you can show me this, you show me the answer, the in between is not there, so you get 0. Because that is not derivation. Derivation means every step should be shown. Okay, remember, yeah, later don't ask me why you don't get the marks for the derivation. Any more questions? If you want to find RMS, how do you do it? That is the equation that you should see here. You derive, that is the equation with the set 2. And inside is a quasar 2, yeah, is a power of 2, the whole equation. This one is rather complicated to derive, isn't it? You have a sine squared. So normally this one is not asked to be in the exam or in the test. Okay, so you need to remember how to calculate the RMS. You can remember directly Vm over 2 for half wave R load. If you want to try also, you can go on, but that one is more to mathematics. Here, normally, this is famous because it's simple. Okay, any question you want to ask? No? Can you try this one right now? This question example says that this is a single phase because you see that it's only one source, right? AC, and it's a half wave. This is only one diode. You should remember that one diode only, half wave. And the load is only R, so it's a single phase half wave R load, right? Normally the picture is not given, so you need to draw it to make yourself clear. So given here the supply V equals to 120 V RMS. Now V is normally here the supply Vs. Vs is 120 in the RMS mode. And the frequency equals to 60 Hertz. These are the information given. How do I calculate the average load voltage? If you're still not sure, what is this average load voltage refers to? V out or V average, both are the same. And the current. So the current is also the average current, I out, or I average, it's the same. Okay, so before we proceed, we have to go back and recall back Ohm's law. You know who is Ohm? Ohm's law says what?
V equal to IR.
V equals to IR. Okay, so you know V, you can R, you know the R is 5 ohm. You can find I, isn't it? Very simple. So now, can you tell me what is V out? V out equals to Vm over, we have just derived it. Vm equals to
M of I.
I. How do I how can I immediately tell the answer? That's why you need this. The cheat sheet. You see that the V out, V out, V out, V out. Yes, you need a summary table so that you can remember them easily. You see that all the V outs are not the same. So here V out for this case is Vm over pi. So you calculate Vm. Hello, there's no Vm given. How do I calculate? How do I know what is the Vm? Vm is 120. Is it correct? So what is Vm?
1.414 times 120.
Let's go back. What is RMS? Am I right? VRMS is Vm over SEEE4433. So Vm equals to SEEE4433 times VRMS. Given 120 RMS, so I need to time with SEEE4433. So can you press your calculator? 120 SEEE4433 divided by pi. What do you get?
54.02.
54 what?
0.02.
What is the unit?
Volt.
Volt. So I am right, 54 volts. Okay, so this one done. And at the same time, you need to find the I current. I current equals to V out divided by R. So it's 54 divided by R is 5. What do I get?
10.8.
10.8. Answer, amps. Okay, another reminder. The unit is very important. If you don't have the unit, normally I will cut half the mark. Okay, 10.8, you put 10.8, okay, you get half the mark. Ampere's key is not there, then half mark is for me. Okay, so I collect more marks for the units. So make sure you have all the units, important, watt, volt, amps. So how to calculate the voltage in RMS? Okay, refer back. What's the equation for RMS? Vm over 2. Okay, again. So what is the average power absorbed by the load? See, the load, just now R, I said R cannot be charged, cannot be discharged. What is the function of R? It only eat and eat. That's why R is fat. Okay, no, R only consume. Okay, it consume the energy. It doesn't produce. So consume here means what? Absorbed. It consumed the power, absorb the power. So how to calculate the power? Here, there's a note here. Power average equals to I. Should I take the average current or the RMS current? Please remember, when you're playing around with the power, it's always, all the time, never happen, never. RMS. Okay? Never take the average. Okay, take the RMS. If you are dealing with AC, because the input is AC, right? So the RMS value is very important here. To calculate the power, you take the I or the V RMS. If you want to take the I, then become I squared R. If you want to take the V, then become the V squared over R. Then you can calculate the power. Answer is given here. You can try. And what about power factor? Power factor equals to, if you still remember, P over S. S is the, what is the name of S? Apparent power. P is the real power. So real power divided by apparent power here. Any unit for the power factor? there is no unit. Because power divided by power, you get no unit, right? The apparent power, please remember RMS and RMS only, given there RMS. So try, all the answers are given. Another note at the bottom here, right? The power of sinus and cosine, right? This one, during the test or final, right? Maybe you can memorize it a bit, because sometimes given as a hint, sometimes it's not given. So if you don't remember during the derivation, you will stuck there. How to convert sine power to x? Okay, it's a waste, isn't it? Hopefully it's given. I'm not sure. The question is not made yet. I got the solution here. You can read it later. We have to go a bit faster now. Ready? We were driving the bicycle just now. Now we're going to take a train. Single phase uncontrolled half wave using RL load. Just now we only have the R. Now you have another new friends coming in, which is the inductor. And you need to know the inductor can be, inductor is a passive component. It can charge and discharge. In other words, it can store the energy. I would like to store it for a few seconds, and after that I can release it. Just now in the previous case, it doesn't happen that way. So if you want to get some hints of how this impact the waveforms, you can see here. We'll start with the first diagram on the top there. This is the input, as usual, sine wave. Sine wave. And you see that the current is actually going up a hill and until the peak, and then it goes down. So if you compare the phase, right, it's actually out of the phase from the input. It is different with the previous case, whereby if you look the current, the voltage is in the same phase from 0 to pi and 0 to pi, same. Because this is only R, constant, nothing, no effect to the output. But if you have RL waveform here, you see that the currents is actually going up to the peak and going down until 0. So this point is known as beta. Anyone knows who is beta here? Do you know dinosaur? Do you think we still have dinosaur today?
No.
No. Why? Because they are?
It's in.
Okay. So beta is beta also same like dinosaur. They are not here anymore. Okay. It's known as the extinction. How to spell extinction? Extinction angle. Extinction angle is the point where it becomes. Who becomes? The current becomes 0. That is the point where we know it as extinction angle. Okay. So why is it the current becomes like this? It's because of the impact of the inductor. If the inductor is bigger, then you expect that this line is going up and delay further. But if the inductor is very small, and then you expect the line is going up and very quickly it goes down. And until very, very, very small, that can be negligible, then you see that the waveform is actually going back to R, same phase. So the size of the inductor here will play important role. If the inductor is big, it will go delay further. If the inductor is small, too small, no impact, then it will be like just R only. Okay, so the slope or the hill will actually going to the right hand side further until it becomes stop 0. Then it's known as the extinction angle. Okay, That is the current. In this case, we will always start with the current, I out. Why? Because if you know the I out, you can draw the V out. Why did that so? Because we are looking at the gradient of the current. What is the gradient of the current from 0 to the peak? Positive. What is the gradient of the current from peak to extinction beta? Negative. So current is obtained by using the voltage of the inductor can be calculated using VL equals to L di over dt. So di over dt is actually the gradient of the current. Okay, di over dt is the gradient of the current. Gradient positive, you get the positive half cycle. Can you see the positive half cycle? Until the peak. And then from the peak to the extinction angle, you got the you got the I put it should be the negative half cycle, negative gradient. Okay, so negative gradient, you get the negative voltage here. Okay, until beta stop lah. Finish the story. This is sine wave, yeah, sine wave. Okay, you finish the sine wave because it stopped at beta, right? So we have to stop immediately with the slash like that. If we go further on, then maybe you can have the sine wave complete. But if it's just at the beta, then we have to stop immediately at the beta. Beta means the current equals to 0 already. When there's no current, no voltage on the inductor. So this is only VL, right? Only one voltage, VL. But then our load, we have VR and VL. They are in series. We have to sum them up. Okay, come back to the story of VR. Just now we say that R, V equals to IR only, right? R is always carries or always follows the waveform of the current. So if the current is this wave like that, so the voltage of the R, voltage drop of the R is the same. Follows the, it follow the waveform of I out. We got VR and VL already. So how do I find V out? V out is actually the sum of VR and VL. Why? Because they are connected in series. Am I right? What is the KVL? Still remember what is the name of KVL? Kirchhoff voltage law. Vs equals to VR plus VL. Vs is the sum of VR plus VL. So VL and VR is actually the load, and the load is V out. We want to find the average or the output voltage of the output is VR plus VL. So the VR plus VL, meaning that we plus, I'll put it as A and B. So this waveform of V out is actually A plus B. So you plus them, then you get this waveform. And this waveform actually is following the input. See, it crossed the pi and it stops where? It stopped at the point where both stops, at beta. So if I don't know A and B, VR and VL, can I draw V out still? Yes. Because you know that the current, when you know the current, you can draw the voltage because the current tells you where it starts from 0, where it stops at beta. So you can plug on the 0, start, stop, beta. You know the 2 points already. And V out, the waveform is always following the sine wave. So in this here, you can always draw the dotted line. You can always draw the dotted line like this. That is the reference, yeah, we call it a reference. So here we start from 0, pi, and then we know that the beta. So what do we do next? Then we know that the current is starting from 0 until beta. So the waveform of the voltage output is also coming up. It follows the waveform, yeah? It follows the waveform until it becomes when? Okay, this point beta, until here it will stop. So we just draw the line like this, straight line. Stop already. So the blue color is the waveform of the V out. How do I draw it? I need to know when it started, when it stopped, following the reference of the Vs, which is the input voltage waveforms. That is V out, the total. Sometimes we need to know that separately, because we know the output is actually consists of two, VR and VL. If we want to know VL, how is the performance of VL and VR individually, then we have to come back here. We should be able to draw them as well, which is the VR and VL. How do we know VL? To draw VL again, you need to know this formula. This is the voltage drop of the inductor. VL equals to L di dt. And di dt is the gradient of the current. So you split them into positive half cycle and negative half cycle. Positive half cycle will give you a positive sine wave. A negative half cycle will give you a negative sine wave. Okay, until the starting and the ending point is still the same, from 0 to beta. And what about VR? Again, VR, we just use Ohm's law. It follows the waveform of the current. So same waveform, different magnitude. So if you want to plus them up, A and B, VR plus VL, you always get V out. Okay, so these three waveforms, you should be able to draw them. Okay, so this dotted line here, the thick red dotted line, actually can be shifted to the right. It can be shifted to the right. How? By making L bigger. If you have bigger L, meaning that the current can be discharged longer, because the L can store longer and discharge longer. If your L is small, then the beta will shift to the left because it finished discharging quickly. Boleh? That is the story of this RL load. Now we want to see the equations, how we're going to use the equations to calculate. So we always start with the KVL. You see that the KVL here, and then we're going to transform them into equations using the first order differential equation. Class, don't worry about that. We're not going to ask you to do this. You learned that in your, what subject is that you learn this first order and second order equation? Okay, so you will end there. Okay, you learned already. Now we're only going to apply them. So you need to know that this equation is actually obtained using the forced response and the natural response. And then what we are interested here is the output of these responses. So from the responses, actually you get this finalized equation. I, the current that flows in this circuit, the one that we say going uphill and going downhill and stop at beta, this I can actually be expressed by this equation. The waveform of the current, output current. Quite complicated, isn't it? You have the omega t minus theta, and then you have omega t over omega tau. Do I need to remember this equation? The answer is yes, you need to remember. If it is not given, if it is given, then you need to remember how to calculate the parameters inside. Let's go one by one. We have the Z. What is Z here? Z is known as? Anyone can help me? What is the name of Z here?
Impedance.
Impedance, correct. What is the unit of impedance?
Ohm.
Ohm, right. Theta is this angle. Now, to calculate the value of the impedance, you get R squared plus omega L squared and square root both of them. You get the impedance. And theta is obtained using the inverse tangent of omega L over R. So this one we need to remember. And what about tau? Tau is the time constant during the natural response. Do I need to remember? Yes, you need to remember because it's one of the parameter inside the long equations. So tau equals to L over R. So there are a few equations that you need to remember. Tau, theta, and Z here, Z here. Vm, you know that is from VRMS. You can obtain that. So if you're not able to remember this long equation, at least these parameters you should know. Because I think if the question come out like that, this equation will be given, hopefully. But the Z, theta, and tau will never be given. You need to know how to calculate them. Okay, so this equation is actually for the RL load half wave to represent the current that flows through the RL load half wave rectifier. Okay, at the same time, you need to know how to draw the waveform as well. Hopefully you can draw it again. You need to draw it again here to remember them. Extinction angle, we already discussed the extinction angle just now. So now we need to know how to identify the extinction angle as well. Where do we start? No. Let's see. Note that the diode remains in forward bias longer than pi, although the source is negative during the duration. Because why? Because the inductor is still able to discharge. During the positive half cycle, you are charging, right? Charge. The inductor can store. During the negative half cycle, no current can flow. But the inductor was fully charged just now and it can discharge. That's why at this point forward is actually by discharging of the inductor. Okay, that's why you can shift to the right. The point when the current reaches zero, this is the point where the beta comes in. It's known as the extinction angle. So if the equation is given like that, so I beta is what? Beta equals to? So you can equate the whole box, right? This is the equation of the current. If the equation of the current equal to zero, is the point when the current become zero. So if you solve that equation equals to zero, you get the beta value. And then for sure, beta is not easily calculated. It's not because you have all these parameters inside. So don't worry. We won't ask you to do the calculation like that. We'll ask you to do calculation that is easily performed using your calculator. So the diode conducts between 0 and beta. There's another term that you need to remember. It's not in the note, I guess. It's known as the, where should I do it? Conduct. You know what is conduct? Conduct means it's working, right? Working or performing. In this case, the current is working from 0 to beta, right? From 0 to beta. So working, conducting, the current is conducting. So there's another term here known as conduction angle. Conduction angle is the angle whereby the current is conducting. So the current is conducting from 0 to beta. So that is the conduction angle. That's all. This one, your original tau equals to L R. And then how to calculate the DC current? You can use the integration, okay, from 0 to beta, because the current is only from 0 to beta. And the equation of I omega t is what? Very long. The I omega t is actually here. So to integrate the whole thing is quite complicated. You need to use what? Calculator. Okay. Do you know how to press calculator? If you need to calculate the I out? Anyone? Anyone? To calculate, yeah? Okay. So, the concern here is how to press the calculator by inserting the long equation here and the integration. Do you know that? If you don't know, make sure you know it. Otherwise, you have to calculate using manual integration. That will take you 1 day to do it. But if you press your calculator, you get it in 2 minutes. But most of the cases, right, because the equation is too long, you press the wrong thing, then at the end you get syntax error. Then you have to press again. So your job is to play around with your calculator because everyone got different model of calculator, right? So it's quite difficult to, let me see if I have the notes for calculating your, where is it? I don't remember where I put it. Let me find it and share with you later. I'm sure I got it. I cannot find it yet. I'll let you know later. Okay, so make sure that you remember that if you want to calculate this, you must use calculator. Yeah, don't waste your time to derive that. What else? RMS also equation. If RMS, right, for all the cases you still remember, you need to know this square root and this one, the power 2. Square root and power 2. But then the equation inside is different, but the formula outside is still the same. Power also, squared R is always RMS. Power factor is always the same. You need to know that this is the parent power using RMS values for the I and the V. So as exercise, you can try this one. You see that the answer is actually very long. This is the Vm over Z, right? The values, sine omega t minus theta plus the values, and then you have the omega t over omega tau, I guess. I also cannot remember. So that's actually very long. Omega t over omega tau. So you need to plug in the omega tau values. Eventually you get 0.377. Now here comes another problem. Radian. Degree. Are they the same? Omega is given in 377 radian per second. If you still remember, you need to convert from radian to degree. What is the relationship of these two? Uh, 1 pi is in the mode of radian. How to spell radian? I guess a T here. 1 pi equals to what? How much of degree? Okay, that's always I get it. Okay, if you don't like 1 pi, maybe you can do 2 pi equals to 360. Also can. Pi equals to 180, and this one is the unit of radian. This is the unit of degree. From here you can do the conversion, okay? Because you see the beta is 201, right? 201 equals to 3.5 radian. How to do the conversion? Using the ratio above there. So this one, the example is not shown the solution. You can try it by yourself. Answers given until you get the all the equations at the back. So you need to press your calculator and get the equation. Okay. Any problem so far? Because we're going to move forward to the controlled halfway. Previously, we talked about the uncontrolled diode rectifier, half wave. Now we want to change the diode into SCR. So what is the impact of changing the SCR? Oh, there's nothing there. If you change the SCR, it means what? You are actually controlling the starting point. Previously, when I turn it on, it's on. Now I change to SCR, control the start angle. What is the start angle just now we say? Here you are. The start angle is known as the firing angle. And how do you control the firing angle? By giving the gate signal. You give the signal to the gate, which is the current that you supply to the gate here. The gate here, you supply the current IG. IG, when I supply the I to the G at the angle of alpha, we know it as the firing angle. So before the firing angle, nothing happened because the SCR is controllable starting point, okay? So this alpha actually can change. You can change the starting point of the alpha. If I start the alpha at 0 degree, can you tell me what is happening? Alpha start at 0, what is happening? If alpha start at 0, I'm coming back to the same uncontrolled rectifier. Because this one start at 0. You always start when you perform the circuit like this. But if I change it to here, SCR, then I have the power to change the starting point. The starting point is angle of firing. And sometimes they call it as a delay angle. So don't be surprised that you don't find firing angle and you find delay angle. They are referring to the same alpha. So delay or firing is the same thing, alpha. If alpha equals to 0, so it is equivalent to the uncontrolled SCR. So it's equals to what? VM equals to, V out equals to VM over pi. Same. Now, if I delay a little bit of this happening, I delay it to alpha, right? So the waveform becomes the red color here, V out. Why? Because from 0 to alpha, there is nothing. So this piece of cake, I need to cut it out because the SCR is still not working. I cut out the piece of this cake. Does it affect my total area under the curve? This curve. This is the input. This is the output. The area of the output, because this triangle cake is being cut away, so the area becomes smaller. The area becomes smaller, definitely the equation will become different. Now we need to derive again. So what is the area? It's 1 over 2 pi because the whole cycle t is 2 pi. So 1 over 2 pi. Let's integrate. Where is the starting point? It starts from alpha. Previous case, it starts from 0. Now I start from alpha. So here at the bottom here, I have alpha. And I want to integrate until pi only. Why not further? Because it's 0. It's not necessary to do integration there. So they're repeating the same thing. Actually, the whole thing is the same. What is different here? Only the starting point. Instead of starting from 0, I now start at alpha. So if you derive it, you get this equation, Vm over 2 pi in the bracket 1 plus cos alpha. If you don't believe it, let's continue with this test. We substitute alpha equals to 0. Do I get the same answer? Okay, alpha equals to 0. Cos 0, what do you get? Cos 0 is 1. 1 plus 1 is 2. 2 divided by 2 is 1. So answer you get Vm over pi. It is still the same. Okay, if the alpha is 0, you get back the same uncontrolled equation. If alpha is not 0, then you have to use the green color box here. Okay, so you have to make sure that you know the initial derivation equation here. Always remember. You need to remember this one if you want to do it quick calculation, but you always need to know how this green color box is obtained from the original integration equation. Okay. Are you still there, or you already lost in the space? We are coming to controlled half-wave rectifier with what? For the RMS voltage. And then what else? RL load. Okay, before we go for the RL load, right? This one is still repeating the same thing. It's just that equation now become a bit different with the blue box and the red box. Again, these are all the equation you need to remember. But to calculate, you need to get the help of calculator because it's difficult to derive. But if you want to derive also, you need to know this, the help of the trigonometry and sine expansion of the sign, because you have sine to the power of 2. Okay, now I'm not sure I should proceed it or not. It's so quiet here. Are you guys still there? It's heavy to digest again, I know. I think we will stop here.